Hi students, in this first video for today, we are going to talk about molecular polarity. Where does molecular polarity come from? Well, now we need to go back and talk about the ideas of our electronegativity difference, our bond polarity, and our molecular geometries. So the first thing we want to discuss is the dipole moment. Remember, when dealing with our polar molecules, we have an electron-rich region, which we color red, and our electron-poor region, which we historically color blue. These are done using electrostatic potential maps created by some very large and difficult calculus that we will not deal with in the course. However, we like to illustrate this using either the cross arrow notation or the dipole positive and dipole negative notation. Another way of looking at this is what we call the Dubai moment or dipole moment. This is equal to the charge times our radius. So we can think about the charge difference between our two species, but because these are shared electrons, this isn't as finite as our electrostatic difference and our ideas of Coulomb's law going back to our ionic compounds. R is going to be the distance between the charges, but historically, this is going to be more or like the molecular radius, and what comes out at the end is normally an estimation. Finally, we will end up getting an idea of the debye. The debye is equal to 3.36 times 10 to the minus 30th coulombs times meters. The important part about the debye is that this is going to give us a judge as to how polar a molecule really is. So the more debye moment you see, the more polar the molecule really is. So how do we determine that a molecule is really going to be polar or not? Well, the nice way of doing this is taking a magnetic field and first off letting the molecule orient itself. As you can see here with a polar molecule, we are getting many interactions that we see with the positive side of one interacting with the negative side of the other. We are going to show you how to do this with the first idea in Chem 120, and this is typically what we call the intermolecular forces. But as you'll notice, these poles start to align themselves. This is done instantaneously, and depending on the strength of the debye moment, this can be done very easily and instantaneously. However, with the magnetic field on, notice that we will start to get the outside influence of our magnetic field organizing our molecules, but internally we still have those positives and negatives attract internally. So, as you can see with the field off, we are allowing the molecules to organize themselves, but then with the field on, we are going to have the outside influence to organize certain molecules, but the rest of them are going to organize internally so that way they become more structured. So now let's look and see it on a molecule level. The first thing I want you to notice is that we have our nitrogen, which in this case is going to be more electronegative than our hydrogen. So it's very important for you to see that the arrows are pulling the electron density away from our hydrogens. But the most important aspect of our NH3 is going to be our lone pair of electrons. Notice that there is a very large arrow pointing in that direction. This is because when you have lone pairs on the central atom, that is negative electron density that is going to have a large volume. In our molecule you see at the bottom, notice that around our hydrogens are very dipole positive, signified in our blue color, while where our lone pair should be in our orbital is very red, and this is going to be highly dipole negative. This is how we result in the dipole moment of 1.46 Debye. Now let us go and look if we replace those hydrogens with our fluorines. So in this case, notice that fluorine is going to be the most electronegative element in our molecule, and we have changed the direction of the arrows from our nitrogens towards our fluorines. While we have our lone pair of electrons still having great electron density with nowhere to go, notice what this has done to my molecule. We have dipole negative locations around all of my fluorines, and now we have less of a dipole negative up where the electron should be. So while we still have a lot of the same components, changing just one aspect of a molecule can determine and change all of its electronic characteristics. This is going to possibly change the reactivity when dealing with using our lone pairs. So, just to look and understand a few of the ideas of our dipole moments, notice that I give you many molecules, its geometry, and finally its dipole moment. If I have HF and it's linear, it is going to be obvious that we are getting a dipole moment directed towards our fluorine. Our pair of electrons are going to go towards our fluorine, and we are going to get a highly polar molecule. That is how we end up with a Debye moment of 1.92. The same is true for chlorine and bromine, but remember, because they are less electronegative halogens, we don't get near the moment. So now let's go ahead and look at our water. If we go and look at our H2O, we are going to have two polar bonds, one from the oxygen to hydrogen going one way and one going to the other. But now the important part are these central atom lone pairs. If you have atoms with lone pairs as your central atom, this can really indicate our polar molecule. It is not a guarantee, but if we look at this with molecular geometry, the important part of all of this will now show you that our lone pairs are not equivalent and not canceling out, and we would have a dipole moment that is going to be negative towards that pairs of electrons. When it comes to our ammonia that we've seen previously, remember that we would have that pair of electrons on our nitrogen, and it would be the same thing. So we're going to come up with a very standard procedure when trying to determine our dipole moment for our molecules. First off, we will not be calculating this. You would need a lot of calculus or a computer to do the approximation. So what we're going to do is use a lot of theory of ideas that you've used previously. One, we're going to draw the molecular geometry with the lone pairs. So as you saw with the water, I drew the Lewis structure, and it looks like those pairs of electrons are canceling out. They are not. So we have to draw the molecular geometry. Then I have to see if there are two highly electronegative atoms in the molecule. If that is the case, we may get a dipole moment between atoms. Finally, if I go to number 3, are there lone pairs on the central atom? As you saw with the water, that is the case. And finally, with 4, we're going to do what is called the symmetry test. The symmetry test means that they're equal and opposite and pulling in opposite directions. So in the case of a molecule like carbon tetrafluoride, you might see this as this. Notice that I have many fluorine carbon bonds that are polar, but they're pulling in opposite and equal directions. So while I drew the Lewis structure, that can help produce this, but if I also draw it in the molecular geometry, you are going to see that it is pulling opposite and equal, and the individual dipoles coming from the bonds are going to cancel themselves out. So here is my carbon tetrafluoride. Notice that the pull is opposite and equal. So this would be a molecule that has polar bonds, but is a nonpolar molecule. So let's try a few examples. Predict whether each of the following molecules has a dipole moment. So let's go ahead and look at our bromine chloride. So in this case, I will have Br and Cl. Now, if you need to go and look at your electronegativity charts, that is understandable. But in this case, we're going to have a bromine at 2.8 while chlorine has an electronegativity of 3.0. We are going to have a very small dipole moment. While this would be considered a nonpolar molecule, we are going to have our arrow drawn slightly to the right. For B, we are going to now talk about boron trifluoride. So in this case, I will have a fluorine attached to my boron, and I have my last fluorine there. Here are all of my lone pairs. This would have the trigonal planar molecular geometry, and you will notice, if drawn correctly with that geometry, that each one of these is going to be pulling out towards the fluorine, and they would be pulling opposite and equal. So the boron-fluorine bond, which while boron has a electronegativity of 2 and fluorine is 4, this is a highly polar bond, but they would cancel out due to the molecular geometry. A better drawing of this would have our fluorine attached to our boron, and now you would see that the resulting vector math would end up canceling out, and we would end up with a nonpolar molecule. So let us go ahead and look at a species that is going to be very important for you when you get to your organic chemistry. This is typically called dichloromethane, or we just signify it as DCM. This is a solvent you're going to use a lot in the lab. One way of drawing this can give you a lot of confusion. So let us go ahead and draw it in one Lewis structure, and this will show you the importance of the Lewis structure and why you can't do this just from the Lewis structure. So I've drawn it like this. Well, if I have chlorine, which is highly electronegative, won't we agree that we would have an arrow of electron density pointing down and to the right? The problem with this is that if I were to have drawn this molecule a slightly different way, and that is not even changing the attachments, but just rotating its molecular geometry, you would think that these would be equal and opposite and pulling in equal ways, and that you would result in a nonpolar molecule. That is not correct. The best way of doing this is going and drawing the molecular geometry correctly. So now what I will do is have my chlorine here. I will now have my chlorine coming down and towards us. And finally, we will have our last hydrogen going down and away. So now you can see where the bi moment would be, and that is coming out towards us and down. So we would have a polar molecule for C. So as you're doing this, there is going to be a feeling that you can do it just from the Lewis structure. You cannot. You want to be able to do it from the molecular geometry drawings. Our final example for this video, which of the following compounds is polar in nature? So now we have to look at our various drawings. So let us go ahead and start with our SCl2. So if I have my chlorines on the outside, my sulfur in the middle, I will have a total of 20 electrons. So in this case, I will put the electrons on chlorine, and now I have a good Lewis structure. But remember, what I want to do in this case is look at it in its molecular geometry. So now with our sulfur, we are going to have 2 lone pairs, and this will be the bent molecular geometry. Because I have 2 lone pairs on my central atom, and they are not canceling themselves out, this would be considered a polar molecule. So for number 1 is a viable possible answer. Let us go ahead and look at number 2. So in this case, we're going to put our bromine in the middle. We have our chlorines surrounding our bromine. And we have to come up with a total number of valence electrons. We have 6 halogens, and each halogen brings 7 electrons. That's a total of 42. So right now I have used a total of 10, and I'm going to put in the lone pairs now. And when you see I have added all of my lone pairs, I will have used a total of 40 electrons, with our 41st and 42nd electron going on our bromine. While the chlorine bonds may be canceled, the lone pair is causing a dipole moment because of its electron density. So right now, we have a possible polar molecule for number 2 as well. Well, seeing that we just did the example for our CF4 back on our description screen, we know that this is a nonpolar molecule with polar bonds. Remember that we can have symmetry. Those fluorines are poling opposite equal, but we are going to disqualify it because of our symmetry rule. So number 3 is not going to be polar. So if I look at my answers, I can get rid of answer E, I can get rid of answer B, and I can all get rid of answer C. So now we have to check the difference between answers A and D, and that comes down to our answer for number 4. In that case, I have H going to my S and another H, and then I would have 2 lone pairs. Notice that this has a similar molecular geometry to that of number 1. Our lone pairs of electrons do not cancel, and for our bent molecular geometry, number 4 is also going to be polar as well. So the correct answer for us in this example is going to be letter D. Answers 1, 2, and 4 are all polar. Once again, number 3 contains polar bonds. However, because of symmetry and them poling opposite and equal, it is going to be a nonpolar molecule. In this video, you saw that we have gone back and used many ideas of electronegativity difference, our molecular geometries, and now the ideas of our lone pairs on central atoms to now determine the molecular polarity. This is going to be an important idea for you going into 120 because you are going to see how that will affect our chemical environment. Have a great day.